Hello, future AP Chemers. This is the second video of the AP Chemistry Summer Assignment. We're taking notes over chapters 1 and 2, and our next topic is matter. So matter is anything that has mass and volume. So pretty much everything around you is matter. Your pencils or pens, your chairs, your food, water, air, your own bodies, all those have mass and volume and therefore are considered matter. So everything around you is matter except for forms of energy. So heat, sound, light, those would not be considered matter. Matter is then classified into pure substances and mixtures. Pure substances cannot be separated by physical means, whereas mixtures can be. So we'll focus on pure substances first. Pure substances can then be classified into elements or compounds. So elements, those are the most basic types of matter, and they cannot be broken down chemically or physically. So if I do a chemical reaction, I still cannot change, a hydrogen atom. It's still a hydrogen atom. The only way I can really change them is by nuclear means, and nuclear chemistry is out of the AP exam, so you do not need to worry about that. There are about 118 elements that have been discovered so far. They're on the periodic table, so if it appears on the periodic table, whether it's the symbol or the name, you know that it's an element. So think like sodium or carbon or hydrogen. Elements can be further broken down into diatomic elements and then others. So diatomic elements are elements that exist in twos. So there are 7 of them: H2, N2, O2, F2, Cl2, Br2, and I2. Those you kind of have to know. And those exist, like I said, as 2 atoms bonded together. So they exist in the form of molecules. And so College Board is really big on particle diagrams now. So this is what a particle diagram of a diatomic element would look like, H2 or O2 or something like that, where you have 2 atoms bonded together chemically. All other elements for the purposes of this class, we're going to say they're monoatomic. They exist as individual atoms. Obviously, you can't separate just one by itself, one atom by itself, but they exist as atoms that are not bonded together. So I'll draw a particle diagram for that. So things like sodium or carbon or potassium, lithium, cobalt, those are all monoatomic and they exist as individual atoms. Just so you know, there are polyatomic elements like sulfur exists as rings of 8, S8. Phosphor exists as 4, so it's tetratomic. You do not need to know that for the AP exam any longer. So unless they tell you on the exam itself, you just assume that they are monoatomic. So those are elements. Now if you take 2 or more of those elements, whether they're monoatomic or diatomic, and combine them together using a chemical change, so you do a chemical reaction and combine them together, then that makes a compound. So they are 2 or more elements combined chemically. An example of that would be H2O or NaCl or H2SO4 or something like that. And here is a particle diagram for it. Remember that if you have 2 different types of atoms, to show that you need to make them either different sizes or different colors or shaded differently or something like that. So this is water. It looks like Mickey Mouse. And it's made up of 2 hydrogens and 1 oxygen. Because in order to make a compound, you combine the elements chemically. If I do a chemical reaction, I can separate my water, for example, into H2 and O2. So I can change it or break it down chemically. So compounds cannot be broken down chemically, but not physically. All right, now what if you combine 2 or more of these pure substances together? So let's say you take 2 elements or 2 compounds or an element and a compound or 2 elements and 1 compound or something like that, any combination, and you combine them together. You can combine them physically, and that makes a mixture. So 2 or more pure substances combined physically, and therefore, because they're combined physically, you can separate them physically. So an example of that is salt water. So if I take some salt water, then I can separate it physically. It's made up of 2 pure substances, salt, which is a compound, and water, which is also a compound. If I boil off the water, that's a physical change, then they separate. And so, again, mixtures can be separated physically. Here's a particle diagram of a mixture. There's a compound and there's an element there. Now, mixtures can be further broken down into heterogeneous and homogeneous. Homogeneous means the particles look, or the solution, or the substance, your mixture looks the same throughout. Homo means same. Whereas heterogeneous, hetero means different, so it does not look the same throughout. So you might see some precipitate at the bottom, or something being suspended throughout, or at the top, or something like that. If it's heterogeneous, so for example, like mud water, where the mud settles at the bottom, or pizza, or orange juice with pulp, those are all heterogeneous. If it's heterogeneous, then we call it a suspension. And part of the reason why the particles don't mix evenly is because the particles are pretty large. Homogeneous, where it's the same throughout, could be split up into either solution or colloid. And so to the naked eye, the particles look like they're evenly distributed. Everything's the same throughout. Solutions tend to be a little bit more transparent or clear, not colorless, but clear. You can see through it. So salt water, for example, Kool-Aid, things like that would be a solution. Whereas colloids tend to be a little bit cloudier, like milk or Jell-O or shaving cream. And the reason for that is because solutions have smaller particles, whereas colloids kind of have medium particles in between solution and suspension. To separate between those two, because to the naked eye they look both the same throughout, we use something called the Tyndall Effect, which is the scattering of light off of the large particles. And so if I shine a laser through the solution, if you remember last year, you couldn't see the light in the solution itself. But if I shine it through a colloid, you can see the light scattering off of the particles in a colloid and also of a suspension. So suspension and colloid have positive Tyndall effect. Solution has a negative Tyndall effect. Next we have some terms to review from last year. So extensive properties, these are properties that depend on the amount, like volume, length, surface area. So if I put more of it, then, it changes. Intensive properties are things that are independent of the amount. So it doesn't matter if I have just a little bit of it or if I have, a ton of it, it should be the same. So color, odor, reactivity, density, those are all intensive properties. They do not depend on the amount. Then we have physical and chemical properties. So physical properties are properties that you can observe without changing what the chemical composition is. So for example, I can notice that the color of a pen is red. I did not change what the pen is made of. I could observe an odor or a texture, or I can observe the density or the mass or the melting point or the boiling point. I can observe all these without changing what the substance is. Whereas a chemical property is a property that if I observe it, I'm going to change what the substance is. For example, if I observe that something's reactive, that means that I've observed it react and it had turned into something else. Or if I observe that it's flammable, that means it's burning, and because it's burning, it's turning into something else. Same thing with flash point. The flash point is the lowest temperature at which a substance can ignite. So if it's igniting, that means, again, it's burning and turning into something else. Distinguish between properties versus changes. So a physical change is a change that does not affect the chemical composition of the substance. For example, if I dissolve sugar in water, I have not changed what the formula for sugar is and what the formula for water is. They're the same substances. So the dissolving process, that's a physical change. The solubility is a property. Opening a can of soda, I have not changed what the substances are. Boiling ethanol, it's still ethanol, whether it's liquid or gas. Cutting a piece of magnesium, it's still magnesium, whether it's in a big strip or small pieces. A chemical change, however, is a change that alters the chemical composition of the substance. For example, if I burn the ethanol, then it turns into carbon dioxide and water. It's no longer ethanol. If I bake a cake, if I neutralize HCl with baking soda, then I'm doing a chemical reaction changing my substances. If I see a metal corroding or rusting, then it has oxidized. So these are chemical changes. Now, something to note here, you'll see throughout my notes and study guides, you'll see boxes here, these are pretty important. If you see something in a box, make sure you read it over and over again and you know it for sure. Sometimes there are little tips that are very helpful. Sometimes it's a note saying, hey, this is no longer on the AP exam, just so you know, so you don't need to memorize it or study it. Sometimes it's a common misconception that I point out. So the boxes are really important. So let's look at this here. It says, during a physical change, the intermolecular forces are disrupted or overcome. For example, if I boil water, that separates one water molecule from another water molecule, but does not break any individual bonds in the water molecules. So dissolving, boiling, melting, and other phase changes are physical changes. And so again, physical changes disrupt or overcome the intermolecular forces. There's an attraction between the molecules. I overcome that attraction in order to boil it or dissolve it or something like that. Whereas in a chemical change, the bonds are broken and new bonds are formed. So you talk about breaking of bonds and forming of bonds in a chemical change. You talk about intermolecular forces being overcome in a physical change. So that's very, very important. It's something that graders of the AP exam always comment on, that people mix up. So when you're doing a physical change, you always say, I overcome the intermolecular forces. When you're doing a chemical change, you always say breaking or forming the actual bonds. All right, the next 2 pages are techniques in order to separate mixtures. A lot of these you are familiar with, some of them you're not. So we are actually going to talk about these in class in August. So we'll skip through those 2 pages and go to page 8 of your study guide. So the next topic is going to be a review of atomic structure and atomic history. The father of modern chemistry is Antoine Lavoisier. He was French. He wrote the first book of modern chemistry. And he came up with basically the law of conservation of mass when it comes to chemical reactions. So he did chemical reactions, he massed the reactants, massed the products, and found that in a chemical reaction, mass cannot be created or destroyed. So College Board that writes the AP Chem exam are going away from memorization. So you do not need to remember any names or any history or any dates or anything like that, but you do need to understand the concepts. So, they'll never ask you, hey, what is the law of conservation of mass? But doing a chemistry problem might rely on you knowing that the total mass of the reactants need to equal to the total mass of the products, for example. Okay. Joseph Proust, he came up with a law of definite composition by mass, and so he said that if you have a given compound, it's always going to contain the exact proportion or percentages of elements by mass. So a given compound always contains the same percent or proportion of each element by mass. For example, if I have water, whether I have a drop of water or a kilogram of water or a tub full of water, water will always be 11% hydrogen and 89% oxygen by mass. So if I take, the mass of the hydrogen in my compound, the mass of the divided by the total, that's going to be 11%, and for oxygen it'll be 89%. All right, John Dalton, he's a big deal in chemistry. He came up with his atomic theory, which for the most part is still true. Again, they will never ask you to state Dalton's atomic theory or his name or anything like that, but you do need to understand the concepts there. So his first statement says that elements are, there's a typo there, are made from tiny indivisible particles called atoms. All atoms of a given element are identical. The atoms of a given element are different than those of any other element. Compounds are formed when atoms combine. A given compound has the same relative number and type of atoms. So H2O, for example, is always 2 hydrogens to 1 oxygen. And atoms are not changed in a chemical reaction. There are 2 words there that have an asterisk next to them. That means that these are no longer accepted. So, for example, he said that everything is made up of atoms and those are indivisible. That's not true anymore. We do have subatomic particles that the atoms can break down into. And then also that atoms of a given element are identical. That's not true because we also have isotopes. Next is law of multiple proportions by atoms. So what that means is if the same elements form two different substances, the ratio of the atoms in these two different substances is off by a simple whole number ratio. So for example, hydrogen and oxygen can combine in a 2-to-1 ratio to form water, or they can combine in a 2-to-2 or a 1-to-1 ratio to form hydrogen peroxide. Again, you do not need to memorize any of this stuff. You just need to be aware and understand what these things mean. No memorization on the AP exam. A little bit about the history of the atom itself and how we knew what's inside of the atom. So J.J. Thomson, he came up with the cathode ray tube and discovered the electrons there, and he determined the mass-to-charge ratio of electrons. Then Robert Millikan did his oil drop experiment. He determined the charge of the electron. Rutherford, with his gold foil experiment, he was able to detect the nucleus, and so he said that the atom is mostly empty space with the electrons around, and then there is a very tiny dense nucleus inside that has most of the mass, and we figured out that it was the protons and the neutrons inside there. Chadwick was the person that detected and discovered the neutron. So again, you do not need to remember names or anything like that, but you do just need to understand what happened. All right, nuclear symbols. So if I have an element X, X is not a real symbol, but if my symbol was X, each periodic table is published in a different way, and there's always a key to tell you, which one is the atomic mass, which one's the atomic number, and so on. But when we write them out, the atomic number always goes on the left bottom side, or the left bottom corner, and then the atomic number, the atomic mass goes on the upper left corner. The atomic number, so Z for short, Z tells you the number of protons, and that identifies the element. So if you have an atomic number of 6, that means you have 6 protons, and as long as it has 6 protons, it's always going to be carbon, no matter how many electrons or neutrons it has. So the atomic number Z is protons, which tells you what element it is. The mass number, A, so it's called atomic mass or mass number, that, which goes up here, that gives you the number of protons plus the number of neutrons. And the mass of the atom is mostly in the nucleus because the protons and the neutrons each are about 1 atomic mass unit, not exactly, but close to 1, whereas an electron is 2,000 times less than that. And so, yes, the electrons have mass, but the bulk of the mass is in the nucleus with the protons and the neutrons. The electron's mass is almost negligible unless you have, a huge number of electrons. So if you wanted to know the number of protons, neutrons, and electrons in a given atom, the number of protons, you get that from the atomic number, which will either be given to you right here, or if they tell you, it's carbon, then you look it up on the periodic table and you look at the atomic number there. The number of neutrons is going to be the mass number minus the atomic number, and the mass number, again, is either going to be given to you if it's a certain isotope, or you can look it up on the periodic table. And then the number of electrons is equal to the atomic number minus the charge. So if it doesn't have a charge, then it's just the atomic number, which makes sense. If it's neutral, that means the protons, which are positive, are equal to the electrons, which are negative. If it does have a charge, then you subtract the charge from the atomic number to get the electrons. Elements have different isotopes. You know that isotopes are where you have atoms that are similar in everything except for the number of neutrons, and therefore they have a different mass. We will talk about isotopes and something called mass spectroscopy in August because we have never talked about mass spectroscopy. It's a new topic, and so we will discuss that in class in August. So we'll skip through this page and a half here, and we'll go to molar mass next. All right, so hopefully you remember what a mole is. A mole is a number. It is a huge number. 1 mole is 6.022 times 10 to the 23rd particles. And you can have a mole of anything, but because it's so big, usually we use it for atoms or molecules or formula units or something like that. So what's so great about this number, which we call Avogadro's number, is that if you look at the periodic table, the mass on the periodic table is the mass of one atom, if you take it in units of AMUs, atomic mass units. So carbon, for example, one atom of carbon would have a mass of about 12 AMUs. Or you could use that same number for a whole mole, and you use it in terms of grams or in units of grams. So the mass of one whole mole of carbon atoms is about 12 grams. So again, the mass on the periodic table is either the mass of one atom in atomic mass units, AMUs, or the mass of one mole in grams. So that's why this number is so great and easy to use. So let's try some problems here with molar mass. So if I wanted the mass of one carbon atom, if I wanted it in AMUs, I would say it's 12.01 AMUs. If I wanted it in grams, then I can do a conversion. So I'm going to start with one carbon atom. On the bottom, I want to put the same units. So a carbon atom. On top, I will put moles. 1 mole is 6.022 times 10 to the 23rd atoms. So my atoms of carbon cancel. I get to moles, and then I say 1 mole of carbon is 12.0 or 0.01 grams, depending on how many sig figs you need there. And so that gives me 1.99 times 10 to the negative 23rd of a gram. All right, let's try some more problems. So it tells us we have 2.25 grams of barium nitrate. We want to know how many moles of barium nitrate are present. So let's for fun figure out what barium nitrate is. So barium is Ba2 plus, nitrate is NO3 minus, so barium nitrate is BaNO3 2. All right, so we want to know how many moles. So I'm going to write down what I have, the 2.25 grams of barium nitrate. And on the bottom of my conversion factor, I'm going to put grams of barium nitrate so they cancel. And on top, I'll put moles of barium nitrate. And to get the relationship between moles and grams, I use the molar mass. And so 1 mole of barium nitrate. For the grams, I add them up on the periodic table. So I add a barium, which is 137.3 grams per mole. Then I add 2 nitrogens, which are 14 grams per mole each. And then I add 6 oxygens, which are 16.0 grams per mole each. Altogether, I get 261.3 grams. My grams cancel, and I end up with moles. I get 0.00861 moles of the barium nitrate. All right, next I want moles of barium. So I have two options. I could either start over with this, get to moles of barium nitrate, and then do another step to go from moles of barium nitrate to moles of barium, or I can start with my answer that I got here. So that's what I'm going to do. I'm going to start with my answer from the first part. So I started with the 0.00861 moles of barium nitrate. Did a conversion factor on the bottom. I put moles of barium nitrate. On top, I put moles of the barium ions. Now, just a little tip here. Make sure you distinguish between ions versus atoms versus molecules. So if you just wrote moles of Ba, that would not be correct. So make sure that you write, if it's ions, then you show that it has a charge. Anyway, for every 1 mole of barium nitrate, there is 1 mole of barium, and so I get the same answer, 0.00861 moles of my barium ions. Next question asks for moles of nitrate ions. So again, you can start from your original 2.25 grams, or you can start from your moles of barium nitrate. I will choose to start with the moles of barium nitrate. There's all kinds of different ways to do this. Again, on the bottom, I'll put moles of barium nitrate. And on top, we'll put moles of the nitrate ions, which are the NO3 minuses. And for every 1 mole of the barium nitrate, I have 2 nitrate ions, or 2 moles of nitrate ions. So when I multiply this through, I get 0.0172 moles of NO3 minus. Next one is number of oxygen atoms. Again, you can start with your 2.25 grams of barium nitrate. You can start with the moles of barium nitrate. You can start with the moles of nitrate. Whatever you want. I will choose to start with the moles of barium nitrate again. And on the bottom, I'll put moles of barium nitrate. On top, I will go with moles of oxygen first. I can't go from moles of one substance to particles or atoms of another substance. So I have to go to moles first. For every 1 mole of barium nitrate, I have 6 moles of oxygen. And then I can say for every 1 mole of oxygen, I have 6.022 times 10 to the 23rd atoms of oxygen, and that gives me at the end 3.11 times 10 to the 22nd atoms of oxygen. Last question here says how many ions of nitrate are there? So you can start with moles of barium nitrate, you could start with the grams. I will start with the moles of nitrate ions. To me, that's just the easiest way to do it, but you can start anywhere really. On the bottom, I'll put moles of nitrate ions. On top, I will put NO3 ions, NO3 minus, I should say. And for every 1 mole of nitrate, I have 6.022 times 10 to the 23rd ions. And this gives me, I'll write in a different color because it's hard to see here. It's getting crowded. 1.04 times 10 to the 22nd nitrate ions. And that's my answer. All right, let's take a look at the next question. It says the density of aluminum is 2.7 grams per centimeter cubed. How many aluminum atoms are in a piece of aluminum foil measuring 0.18 meters by 12 centimeters by 1/10 of a centimeter? So at first glance, it's like, what does that have to do with moles? But let's see if we can figure this out. So they give us the density, and they give us the dimensions. From the density and the dimensions, we can probably figure out, so from the dimensions, we can figure out the volume. Density is mass over volume, so using both, we can maybe figure out mass, and then convert it to moles, and then to atoms. So let's try that. So first, something that is bothering me here is the units are different. They give us one dimension in meters and two of them in centimeters. What do I want to convert to? Do I want to go to meters for all of them or centimeters in all of them? Well, you look at your other numbers that you're given and the density in centimeter cubed, so you want to convert all of them to centimeters. So this one will be converted to 18 centimeters. So let's do that. So 18 centimeters by 12 by 10th of a centimeter. So when I multiply those together, I get the volume in centimeters cubed. If you want to stop and calculate that and move on to the next step, you can. If you want to say density equals mass over volume, so find out the answer from that calculation, plug it in here, plug in the density to figure out the mass. Before you move on, you can. I like to use my units to figure out where I'm going, and so I am just going to say, well, all of this is centimeters cubed, and so I will put centimeters cubed at the bottom to cancel, and I will put grams on top, and I know that it's 2.70 grams per centimeter cubed, so that means that's 2.70 grams for every 1 centimeter cubed. Again, if this bothers you, you can just plug it into the density equation and get what the mass is. But this way I get the mass and they can just keep moving on. I don't like to use my calculator as much. I like to just keep it till the end. So at this point I have grams because the centimeter cubed cancels. So I'm going to put grams of my aluminum here, moles of aluminum here, and the molar mass of aluminum is 27.0. So 1 mole is 27.0 grams. At this point, my grams cancel and I end up with moles. I'm looking for atoms, so my last step will be to put moles of aluminum at the bottom, atoms of aluminum on top, and to go from moles to particles of the same substance I use Avogadro's number. So 1 mole and then 6.022 times 10^23 atoms. And altogether, I end up with 1.3 times 10^22 atoms of aluminum. All right, let's look at the last problem on this page. It says I have 0.25 moles of iron 3 oxide. Anybody know what iron 3 oxide is? It is rust. Rust is the common name. And I want to know how many grams of iron are in there. So I'm going to write down what I have. So iron 3 oxide means it's Fe3 plus and O2 minus, so Fe2O3. So I have 0.25 moles of Fe2O3. On the bottom, I will put moles of Fe2O3. And I can't go directly to grams of iron. I have to go to moles of iron first. And so 1 mole of Fe2O3 has 2 moles of iron, and then I can go from moles of iron to grams of iron. 1 mole is 55.8 grams of Fe, and I end up at the end with 28 grams of Fe. 2 sig figs because 0.25 had 2 sig figs. All right, next is nomenclature rules. So last year we spent a whole chapter, it was chapter 9, about nomenclature. Nomenclature is actually out of the AP exam because they say it's prior knowledge. So what that means is you need to know it, but it's not going to explicitly be tested. So they're not going to say, you know, what is the formula of iron 3 oxide? But you might need that knowledge in order to do something else. So with the IUPAC naming, IUPAC stands for International Union of Pure and Applied Chemistry. That's a system how we name things. We separate compounds into, or at least binary compounds, into molecular and ionic, and then acids. If it's molecular, that means that it's covalently bonded, or you can tell that because you have two nonmetals bonded together. You start by writing the name of the first element that's on the left side, and then you write the name of the second element but change the ending to "ide," and then you use prefixes for both of them to indicate the number of atoms. So 1 is mono, 2 is di, 3 is tri, then tetra, penta, hexa, hepta, octa, nona, and deca. Usually the mono you don't use for the first element, but you do use it for the second element. So for example, carbon monoxide would be CO. Or CpCl5, for example, would be phosphorus pentachloride. H2O would be dihydrogen monoxide, and so on. If you have something that's ionic, so you know that it's ionic because you have a metal bonded with a nonmetal, then you do the first two steps similar to the covalent. So you write the name of the first element, which is usually your metal. Then you write, we'll get to that in a second, the name of the second element, which is the nonmetal, end it with "ide." Unless it's a polyatomic ion, then you write the ending of it. So if it's sulfate, you leave it as 8, for example. Then you check your metal. If it is in group 1, group 2, or aluminum, zinc, or silver, you're done with the name. If it's not, then you put parentheses with Roman numerals, and the Roman numerals tell you what charge your metal is. So for example, if I have NaCl, that would just be sodium chloride, because sodium is in group 1, so I do not need parentheses. But if I have FeF2, then that would be called iron 2 fluoride. The charge of the iron in this case would be +2, and so that's why it's iron 2 fluoride. For acids, they have a different way of naming. So you look at, an acid is basically something that's covalently bonded, but it starts with hydrogen. And something magical happens when you put it in water. It actually ionizes. So it's covalent, but then it ionizes when you put it in water. So what you do is you look at the non-metal end. So sometimes that's just a non-metal, sometimes that's an anion. But you look at the part that's not the hydrogen. And if you would normally call it something with 8, then what you do is you write that, but change the 8 ending to "ic" and follow it by the word acid. For example, if you have H2SO4, so the SO4 part, that's sulfate, so you change it to "ic", so it'll be sulfuric and then acid. If it ends with "ite", so like H2SO3, SO3 2- is sulfite, so you change the "ite" ending into "us", and then follow it by the word acid, so it would be sulfurous acid. And then if it ends with "ide", so for example, if you have H2S, so S2- is sulfide. So what you do is you start it with hydro, then you end it with "ic", and then you follow it by the word acid, so hydrosulfuric acid. Again, this is not a very big deal because it's out of the AP exam, but you just do need to be familiar with it. So practice a little bit, but it's not as big of a deal as it was last year. Now, if you are going from the formula, from the name to the formula, so you're doing the opposite, here's what you do. So if it's covalent, you write the symbols of both elements, and then the subscripts will be given to you by the prefixes. So no work really much required here. If it's ionic or if it's an acid, then you write the symbols for both elements or polyatomic ions or whatever they are, and you use the charges to make it neutral. So for example, if I tell you I have if I have dihydrogen monoxide, that's covalent, so I hear hydrogen, I hear oxide, and dihydrogen, so 2, mono, 1, so H2O. That's covalent, pretty easy. If I tell you I have sodium oxide, that's ionic, so you have to make sure that you balance out your charges. So what you do is you look at the sodium ion, it's +1, your oxide ion is 2 minus, so to balance out the charges you need 2 sodiums and 1 oxygen, so Na2O. All right, some more definitions or words that you need to be familiar with. So molecular compounds, those are covalently bonded compounds. They are made up of atoms that share their electrons together. Covalent, co means together, valent means valence electrons, so they're being shared. Ionic compounds are made up of ions, that's why they're called ionic. That's where your atoms have lost or gained electrons, so that's why they become charged and ions. If you have a compound, you can get the empirical formula for it, which is your lowest whole number ratio, I should say ratio of atoms or ions. If you have a molecular formula, that means it's multiples of the empirical formula. So when we write a chemical formula, that's the molecular formula. That's the actual true formula for your compound. An empirical formula is a simplified version of the real formula. The reason why we would ever have an empirical formula is sometimes we find unknown substances. We don't know what it is, and so we put it like in a mass spectrometer or a gas chromatogram or something like that, and we analyze it, and so sometimes it gives us percentages or ratios, and so we can only find the simplest whole number ratio as opposed to what it really is. Binary compound means that it's a compound made of 2 elements. Molecular compound, like we said, means it's covalent. Ionic compound means it's ionically bonded, it's made of ions. Organic compound means that it's made up of mainly carbons and hydrogens. Hydrate, if you remember from last year, a hydrate means it's an ionic substance that has water trapped in its crystal. Last thing we're going to end with for the notes today are the law of definite composition, which we kind of had already talked about earlier. It says that all samples of a compound have the same percent for composition by mass. If you remember a couple of pages ago, that was Joseph Proust that said that. So if I wanted to determine the percent composition of aluminum sulfide, that means I want to determine the percent of each component. So in this case, this is a compound, so my components in this case would be the elements. So I want to know what percent of nitrogen there is, what percent of sulfur there is, what percent of hydrogen there is. If my substance was a mixture, and I want to know the percent composition, that means I want to know the percent of each of my pure substances within that mixture. Anyway, let's try to do this one here. So ammonium sulfide would be NH4 2S. That's because NH4 ammonium is +1, sulfide is 2 minus. So if I wanted percent composition, that means again I want percent of each of the components. In this case, that's nitrogen, hydrogen, and sulfur. Percent of anything is going to be the mass of that component divided by the total. So the first thing I'm going to do is I'm going to find the total mass of ammonium sulfide. Now they don't give us any numbers whatsoever, so you can look at any amount that you would like. That's the whole point of the law of definite composition, is that it's going to be the same percent nitrogen in ammonium sulfide, whether you have a gram of it or 100 grams of it or a ton. So the easiest way is to look at 1 mole. So in a 1 mole sample of ammonium sulfide, my total mass would be, I'd add up 2 nitrogens, 8 hydrogens, and 1 sulfur. So in a 1 mole sample of NH4 2S, if I wanted to calculate the percent nitrogen, that's going to be the mass of nitrogen over the total. So if I had 1 mole of NH4 that means I have 2 moles of nitrogen. So 2 times 14 over my total. So if you add up 2 nitrogens, 8 hydrogens, and 1 sulfur, you get 68.1. And then times 100%, of course. And so that gives me 41.2% nitrogen. Now, that is going to be true for 1 mole. That's going to be true for any quantity, though. So if I had just 1 gram of ammonium sulfide, I'd still have 41.2% of that gram as nitrogen. If you wanted to do the same thing for the other ones, so percent hydrogen. So I'd say 8 times 1.0 grams over the 68.1 grams times 100%. That gives me 11.7% hydrogen. And percent sulfur, 32.1 grams over 68.1 grams times 100%. And this gives me 47.1% sulfur. All right, we are going to stop here, and we will do the rest of the notes in August. Looking forward to seeing you all.